Earlier we learned that light behaves as both a wave and a particle. When light behaves as a particle, we call it a photon. Now later, when we studied subatomic particles, we saw that matter can also behave as both particles and waves. And so here, I'd like to focus on the wave-like behavior of matter. The starting point for this is Einstein's most famous equation, E equals mc squared, which really just tells us that matter and energy are alternate forms of the same entity. Next, if we take the Planck equation, E equals h nu, which tells us the energy of light from its frequency, or equivalently, E equals hc divided by lambda. And combining these two equations, we see that we get mc squared equals hc divided by lambda. Now you'll notice that one speed of light on the left-hand side cancels with the speed of light on the right-hand side. So rearranging this equation for lambda, the wavelength, and substituting the speed of matter for the speed of light gives us the de Broglie equation, which states lambda equals h divided by mu, where lambda is the de Broglie wavelength, h is Planck's constant, m is the mass of matter, and u is the speed of the matter. So this really tells us that matter has a wave-like motion, and it gives us the de Broglie wavelength for any particle or matter. In this slide, we have the de Broglie wavelengths for a variety of different objects. In the bottom half of the table, we see the de Broglie wavelengths for a variety of different macroscopic objects. In the top half of the table, we have the wavelengths for 3 different microscopic or subatomic particles. We can see here that the de Broglie wavelengths for the macroscopic objects are all very, very small, especially when we compare the wavelengths to the size of the objects themselves. By contrast, if we look at the subatomic particles, we can see that number one, the de Broglie wavelengths are significantly larger than the wavelengths for the macroscopic objects, and secondly, that the de Broglie wavelengths are very large compared to the size of the object. So the conclusion from this table is that for large objects, the de Broglie wavelength is insignificant relative to the size of the object. However, for small objects, the de Broglie wavelength is large relative to the size of the object. In this question, we are asked to calculate the de Broglie wavelength for an alpha particle, which has a mass of 6.6 times 10 to the negative 24 grams, which is emitted by the radioactive fission of a radium isotope. The alpha particle is traveling at 1.51 times 10 to the 7 plus or minus 0.044 times 10 to the 7 meters per second, and this represents the speed of the alpha particle. So here we're asked to calculate the de Broglie wavelength, which is lambda. So the strategy for solving this problem is to start with the de Broglie equation, which tells us that lambda equals h divided by mu, where m is the mass and u is the speed. Plugging these values into the equation, we see that we have 6.626 times 10 to the negative 34 joules times seconds, which is the value for Planck's constant. For the mass, we have 6.6 times 10 to the negative 27 kilograms. And for the speed, we have 1.51 times 10 to the plus 7 meters per second. Now, before we continue, I'd just like to take a look at the units. So we know that a joule is a Newton meter, and substituting this for SI units, we have kilograms times meters per second squared times meters times seconds. And in the denominator, we have the mass in kilograms, and we have the speed in meters per second. So we can see here that the kilograms cancel, the meters cancel, and the seconds also cancel, leaving us with meters, which is the correct unit for wavelength, suggesting that our calculation is most likely correct. Now, it's also important to remember here that the mass of the alpha particle must be specified in kilograms, so we have to convert grams to kilograms here. Now, next we plug this into our calculator, which gives us 6.64 times 10 to the negative 15 meters as our de Broglie wavelength. However, you'll notice that The smallest number of significant figures in our calculation is 2 sig figs, which we see here. So we'd want to round our final answer to 2 sig figs. So rounding gives us a value of 6.6 times 10 to the negative 15 meters as our final answer. Lastly, it's important to remember that we want to check to make sure that we have the correct units, and meters is the correct unit for wavelength. And that you also want to remember that the mass must be converted to kilograms, as we've seen here in our unit analysis. In this question, we are asked to calculate the de Broglie wavelengths for an electron and a proton, given in part A its speed, and in part B its kinetic energy. Since these questions are quite similar, what I'd like to do is focus on calculating the wavelength for the proton, given its kinetic energy. So question B. Now, the reason I've chosen question B is that it is slightly more difficult than part A, where we're given the speed. The strategy for solving this question is to start with the equation for the de Broglie wavelength, which is lambda equals h divided by m times u, which is the speed of the particle. H is Planck's constant, so we know that value. M is the mass of the proton, and we're given this value. And we are asked to calculate lambda, which is the de Broglie wavelength. So you can see that in order to solve this question, we need to know the speed of a proton. Now, we're not given the speed directly. However, we are given its kinetic energy, and we should remember that we can calculate the speed from an object's kinetic energy using the equation kinetic energy equals 1/2 times the mass times the square of the speed, which we should know from high school physics. So we are given the kinetic energy, and we're also given the mass of the proton, which was shown here. And so all we have to do is solve for the speed, and then plug the speed in to the Broglie equation. Okay, so we're going to try to isolate the speed, and we'll do this by multiplying both sides of the equation by 2. This gives us 2 times the kinetic energy equals the mass times the square of the speed. Then we're going to isolate the speed by dividing both sides by the mass and then taking the square root. This gives us the square of the speed equals 2 times the kinetic energy divided by m. Then taking the square root gives us the square root of 2 times the kinetic energy divided by the mass. So now we're going to plug in the values of kinetic energy and mass of the proton so that we can calculate the speed. So plugging in the values for kinetic energy and mass of the proton into the equation for kinetic energy, we have the square root of 2 times 4.44 times 10 to the negative 15 joules divided by 1.67 times 10 to the negative 27 kilograms. Now before we continue, I'd just like to take a look at the units. So you might remember that a joule is a Newton meter, and a Newton is a kilogram times meter per second squared. And we also have the meter from the Newton meter part of the units. And in the denominator, we have the kilogram, which comes from the mass, in this case, of the proton. So you'll see that in the numerator and the denominator, the kilograms cancel, leaving us with the square root of meters squared per second squared. So taking the square root leaves us with units of meters per second, which is the correct unit for speed. So now plugging this into our calculator gives us 2.305 times 10 to the 6 meters per second as the speed of our proton. Now, knowing the speed, we can now calculate the de Broglie wavelength using the equation for the de Broglie wavelength, which is lambda equals h divided by mu. So plugging the values gives us 6.626 times 10 to the negative 34 joules times seconds, which is Planck's constant, divided by the mass of the proton, which is 1.67 times 10 to the negative 27 kilograms, times 2.305 times 10 to the 6 meters per second, which is the speed of the proton, which we just calculated from step 1. So before we continue, I'd just like to take a look at the units again, where the joule is a Newton meter, and converting this to SI base units, we have kilograms times meters per second squared times meters times seconds. And in the denominator, we have kilograms for the mass and meters per second for the speed of the proton. And we can see again that the kilograms cancel, the meters cancel, and the seconds cancel, leaving us with units of meters, which is the correct unit for wavelength. So plugging these values into our calculator gives us a wavelength of 1.721 times 10 to the negative 13 meters. And you might notice that our answer should have three significant figures because the mass has three significant figures. So rounding to three significant figures, we have a de Broglie wavelength of 1.72 times 10 to the negative 13 meters. Finally, I'd just like to remind you to check the units. So in the step 1, you can notice that meters per second is the correct unit for speed, and meters is the correct unit for wavelength. And finally, it's important to remember that the mass of the proton, in this case, must be converted to kilograms. So you might remember that the mass we were given for the proton was originally specified in grams, and we have to convert this to kilograms in order for the units to work out.